Good afternoon, welcome to video 12 of topic 2 of unit 4, Bohrs Model. This video will be covering the main ideas of chapter 12.2 of book 2. Please complete this reading before class. Here are the learning intention and success criteria for this chapter. Please pause the video and attempt to complete the KS table down the bottom right. Okay, so having a look here, we can see that we've got a bit of knowledge verbs going on. We're about to describe Bohr's model of the atom, explain how light quanta and energy states explain hydrogen emission spectra there. So we're about to describe it, how it fixes Rutherford's model, Rutherford's limitations, and then explain the emission spectra of hydrogen by referring back to Bohr's model. So we need to know what Bohr's model is, otherwise we're not going to be able to do most of this. We need to know what are energy states. If we don't know what an energy state, we can't really use it to explain anything. And finally, what is the emission spectra? Otherwise, we're not going to be able to explain what it is. So, in our previous video, we looked at Rutherford's model and how it had two major limitations. Firstly, it predicted atoms should continuously emit energy and decay within microseconds. Remember, that was due to the centripetal motion of the electrons, and it should just decay. The second problem was that it couldn't explain atomic spectra at all. It was a model of the atom, yet it couldn't explain something that atoms seem to do. Now, Bohr studied under Rutherford, and then after return to Denmark, he eventually developed his own model that solved these two problems. It was based on three key postulates. The first is that electrons exist in stationary states. We'll get to why I've just done that in a second. Now, these are the quantum orbitals seen in the diagram. I'll put the diagram on the next page so we can make it big, but it's in your textbook as well. Now, when they say stationary, they're stationary in that the amount of energy in it doesn't change. Not that the electron's not moving. The electron is still, if you're doing chemistry at the moment, you probably know by now that the electron exists in a probability region. If you're watching this in grade 9, we've talked about orbitals, in that the electrons are sort of buzzing around on rings on certain levels away from certain distances away from the nucleus. Okay, they are still moving. They have some kinetic energy, but they are not giving off energy. That's what they mean by stationary. Now, this dealt with the first problem. Okay, they just said, nah, it just doesn't do it. Didn't explain it. Okay, so Bohr's model does not explain this. It just says, look, this has to be true, otherwise the rest of my stuff here doesn't work. The rest of the model doesn't work. So they went, yeah, it's okay, it's true. They did go and eventually prove it, but that's much later work and not part of Bohr. But you just need to know that that's the first postulate, that it doesn't happen. The second is that the transition between states and orbitals must absorb or emit electromagnetic radiation, which is fairly important. So this means for an electron to go up an orbital, so from level 2 to level 3, it has to absorb energy, normally from light, and being as we've been dealing with photoelectric effect, pretty much everything in this case is going to be about light. And if it goes down an orbital, from 4 to 2, or 3 to 1, or 5 to 2, doesn't matter, it will give off and emits light. But the energy has to be a very specific value. 1 joule more, 1 joule less, and the change will not occur. If it needs 101.2 joules to change, and you give it 101.5, it won't happen. Ionization can still happen. If it needs 100 to ionize and you give it 101, it'll ionize and take the extra 1 as kinetic energy. But if you need 83 to go from 2 to 4 and you give it 85 joules or 84 joules or 83.01 joules, it won't happen. It has to be exact. The final postulate for Bohr was that angular momentum of a stationary electron is quantized. And this is what creates the differing energy levels of the atom in the diagram, and that means atoms only emit certain values of energy. And there is a formula for this. And this is in your formula textbook. You're expected to be able to recognize this about angular momentum. So let's have a look at the image for Bohr's model. Very familiar. We show it to you generally in grade 9, so this isn't terribly different. So this is Bohr's model. Rutherford's model is the one where the electrons are crisscrossing each other, very commonly used on nuclear power plants like in The Simpsons. So here we can see the nucleus in the middle. We have our quantum orbitals, or our energy levels. Generally, you shouldn't call them shells. In physics, you should be calling them quantum orbitals. Here we have a diagram showing that an electron has fallen from level 4 to level 2, and so it has released energy out. If you gave it the exact same amount of energy, it would excite a level 2 up to a level 4, assuming that it hit it. I mean, if it didn't hit it, it's not going to absorb it, I guess. But that's the whole model. You should be able to draw it. I have seen a question like that on QCAA's mock, and you should be able to describe that. As an electron falls down, energy comes off. If electron goes back up, energy must be coming in. Okay. So let's talk about angular momentum for a second. So this equation is all about the concept of angular momentum. This bit on the left, MVR, is how we would work out the angular momentum of something. You don't need to know rotational mechanics, and so you don't need to understand angular momentum past. It's the momentum of something traveling in a circle. That's it. You know what momentum is. You all learnt it last year. Okay? However, in terms of angular momentum, now this is something for curving. Okay? So momentum straight line, angular momentum curving, done. The formula here is showing something really important, that this angular momentum, MVR, is always a whole number multiple, that's the n there, of these constants. H is a constant, 2 is a number, pi is a constant. So h2 and pi, they don't change. Okay? But that n can only be 1, 2, 3, 4. This is what creates those. Let's go back. This is what creates these quantum orbitals. Each of these electrons orbiting around this orbital has some amount of angular momentum. Okay? And they can only be these fixed numbers. Okay? You shouldn't need to calculate with this. There's no solve or calculate verb with this formula, but if you were going to explain Bohr's model, and there is a question where you explain Bohr's model, and you had to repeat the 3 postulates, you got to include this one as part of postulate 3. Okay, remember the formula is given to you. This is in the formula booklet, but use it as oh yeah, I've got to talk about this and da da da. Okay, so that's all we need to say about angular momentum. Oh yeah, there's a descriptor. The symbol for angular momentum is given as L. You don't need to remember it, but perhaps you want to. Now, these fixed orbitals and the energy level transitions from postulates 2 and 3, they explain the emission spectra for hydrogen. Now, hydrogen only emits or absorbs, because remember, if the electron falls in, it gives off, but if the electron goes out from level 2 to level 4, it's got to absorb some energy. A few set colours. Kind of looks like this. Okay, so here's the absorption spectra. If we shone white light, it will absorb those bands. If we heat it up, it will glow, give off only those 5 colours. Each colour, remember, is associated with a frequency. Okay, it's got its own wavelength. That red, I think, is 660 up there or something like that. And then sort of 540. Something like that. And so that wavelength is associated with a frequency because it's light, speed, and we've got that equation, V equals F lambda. And that means each of these colours must be an associated amount of energy through E equals HF. Okay, so we've got a specific wavelength. Wavelength means frequency. Frequency means energy. Remember, these 3 things, whenever we're talking about light, are basically interchangeable because they're only a conversion through a constant. So if you have any of those, you have all 3 of them. So each of these spectral lines, that's what these lines here are called, they're called spectral lines. Each of these spectral lines correspond to one particular quantum change. Now, we saw this equation last video, um, and that the Rydberg equation there models this for hydrogen. So, this one down here, the bottom, okay, let's say that that's when level 3 drops to level 2. If we plug those numbers in, we would get that wavelength there for NF equals 2 and NI equals 3. Chuck that in and we get the wavelength that's coming out of it. Now if it comes out negative, okay, it just means that it's being absorbed rather than being emitted. The next one here would be 4 to 2, then 5 to 2, 6 to 2, 7 to 2. We could plug all those in and get some value. Okay. Now, as I just said, and Bohr did this with his version, okay, if you've got an n equals 2, that's generally going to be for visible light. Okay. There would be some very big... Actually, well, the thing is, you're only going to use this formula for hydrogen. Think of like RH for R for hydrogen, or the H for hydrogen, or the R of only hydrogen. Whatever you're dealing with, energy level diagrams, which we'll see on the next page, or anything to do with the Rydberg equation, if one of your levels is 2, then it's probably going to be visible light. Okay. I have seen some questions that imply knowing that can help you. It's not required. It's not something that's going to be asked of you. The names that we're about to see don't appear anywhere in the syllabus, but it might be something just useful to have that knowledge there, that if you're dealing with quantum stuff and they're saying it's visible light, let one of the n's equal 2. So let's have a look at an energy level diagram, because this wouldn't surprise me if you see it on the exam. This is a very, very thoroughly labelled energy level diagram from the textbook. It is unlikely you'll see anything exactly like this, but there will be certain features. Down the left here we can see our n values. There's our quantum orbitals. Okay, n equals 1. There's our lowest electron level, our lowest quantum energy level. N equals 2, n equals 3, 4, 5. Okay. Down on the right, you can see the energy for each level. Now, the way to read this, okay, you read it as the energy needed to go from wherever the 0 is, and it doesn't matter if it's written in joules or electron volts. I'll show you one in electron volts in a second, to get to that orbital. To work out the energy to go between orbitals, take the difference in the numbers. So, if I want to go from infinity, that is not part of the atom, down to n equals 1, I will give off 21.7 times 10 to the negative 19 joules. If I only fall down to energy level 5, I would give off 0.87 times 10 to the negative 19 joules. If I was at level 3 and fell down to 21.7, I would take the difference first. 21.7 take away 2.41. So what would that be? 21.3, about 19.3, 19.29 times 10 to the negative 19 joules. So what we're going to do is take the difference. Doesn't matter how this is presented. If you're working at the change between levels, take the difference. And if you think about it, like, okay, if I was going from 0 down to 1, well, I would read this 21.7 take away 0, 21.7 times 10 to the negative 19 joules. But the opposite's also true. If I needed to get from 1 to 2, here you go, 1 up to 2, I would have to give it 21.7 take away 5.43, so that's going to be what, 21.17, 16.17. Okay, so I'd have to give it 16.17 times 10 to the negative 19 joules. Okay, if it fell back down, it would then give off 16.17 times 10 to the negative 19 joules. Okay, all you've got to do is take the difference. Walding does go a little bit deeper and give you this idea of the relationship, but that's not in the formula booklet, and that's something that can only really work on hydrogen. And if they're going to give you hydrogen, they'll give you the actual numbers, so don't worry about it. So this one here is given in negative to show the energy change would be released going from infinity down to the level. You can get them the other way. Here's one that goes the other way. Okay. A couple of things to note. Firstly, here it's in electron volts instead of in joules, which does make it easier to do the difference in your head quickly, which is why electron volts are often used. Do note if you were going to have to work out the frequency or the wavelength, you would have to convert that electron volts to joules before you got to do anything with it, though. So if you were just asked what energy is being released or what energy is needed, and you're asked to give an answer in electron volts, just take the difference. If you're asked for an energy in joules, you've got to do conversions. Before or after taking the difference doesn't matter. If you had to work out the frequency or the wavelength, you definitely have to convert to joules first. That formula E equals HF only works in joules. But this one reads a bit differently. So here it's saying, well, to go from 0 to 2, from 1 to 2, we have to give it 10.2 electron volts. Okay? But the opposite's also true. To go from 2 back to 1, it would give off 10.2 electron volts, and then we could convert that to joules. And we'd find the numbers would match. Okay? The numbers would match. So they're not going to it's not going to give you anything different. It's just how it's presenting it is different. And ultimately, so from 0 to n equals infinity, 13.6 electron volts would still be 21.7 times 10 to the negative 19 joules. Because remember, we're multiplying it by that 1.6. Okay. Let's see, is there anything else I need to give there? No. Let's do some examples here. So if you would go from level 4 to ionization, so to release the electron, we would take the difference between infinity and n equals 4. That would be a difference of 13.6 to 12.8, so 0.8 electron volts would be required. If something fell back in from infinity and stopped at level 4, it would give off 0.8 electron volts. If it fell from level 4 to 2, 12.8 take away 10.2 is 2.6, so it would give off 2.6 electron volts. I don't really worry about doing final take initial all the time. I just look at the difference and then I put it into words. You just need to know as you fall into an as you fall into an atom, the electron gives off energy. How much energy is just the difference between these levels. Now, let's have a look at this really carefully for a second. At the top of that hydrogen energy level diagram, and the one in the text, there are a set of names written across the top. Now, the names are not in the syllabus, I did say that earlier, but you should take note that the Bohr series, which is where things fall to n equals 2. So Lyman falls to n equals 1. Bohr was studying when it falls to n equals 2, the visible light stuff. They didn't have really great stuff for detecting the UV stuff there, so they weren't focusing too much. Passion is mostly infrared, and Brackett and Pfund are very high as well. But the Bohr series is generally when an electron in any atom falls to n equals 2, and it's mostly visible light. So it's worthwhile just keeping that little fact there memorized. So let's do an example. Firstly, determine the energy of an electron in both the fourth and second quantum orbitals of the hydrogen atom. So we're going to have to go back and look at that picture and read that question. Excuse me, I'll read that question again. Where am I looking at? Okay, so we need fourth and second. Fourth and second. Now, you could use the, what's what I'm looking for? The energy level sorry, I'll just bring it up for a second. This formula here, we could use this, but you can also just use it directly off the thing. So if you chuck your numbers in there, so if we go negative 21.7 times 10 to the negative 19, and we divide it by 4 to the power of 2, you get that number. And for n equals 2, you divide it by n to the power of 2, you get that number. But the thing is, this formula is not given to you in the syllabus. It is, sorry, you are expected to be able to read an energy level diagram. So that's what we're going to do. We're just going to read directly off the diagram. I believe the image is on page 336. So, N4, let's see, how am I going to write this? Energy at N equals 2 equals negative, I'm just going to put the whole number, 5.43 times 10 to the negative 19 joules. And energy at N equals 4 is 1.36 times 10 to the negative 19 joules. And we could use that electron volt picture one as well, and would get the same numbers. So that's all we need for this first one. The first question is just asking what is the energy in the electron, and you just need to read it. Bring it back in for us. Make sure we can see that. Yep. We are just reading it directly off the side of the text here. Okay, you don't need to do the calculations that Walding does. You just read them straight off the energy level diagrams, because that formula that he presents only works for hydrogen. There is a version of it that works for hydrogen-like elements. That means elements where there's only one electron that you have to worry about because it's a huge ion. However, and it has an extra Z scaling factor to do with the atomic number. But at the end of the day, that's not within the scope of the syllabus, and it's only an approximation anyway under a very, very extremely weird circumstances. At the moment, energy level diagrams for atoms, for any element, are determined experimentally. It is not something that is has a basic formula behind it yet. So let's just practice reading off the diagram, because why, it's a lot easier. All right, second question is asking, calculate the frequency of energy emitted, okay, when an electron jumps between these orbitals. So we want to calculate the frequency. And remember, it's all about the energy. So the frequency comes from the change of the energy. It will be the frequency. Now, change of energy, well, that's going to be the change when it goes between these two orbitals. Does it say which direction it jumps between the frequency of the energy emitted? So it goes from 4 down to 2. Alright, so we need to have... Yep, so 5.43 take away 1.36, and they're both times 10 to the negative 19. 5.3 is going to be 4.07 times 10 to the negative 19. It will be a negative in this case because it's being emitted. I'm just going to put there brackets. Emitted. And we want to convert that. We want to convert that into a frequency. So F will equal E divided by H equals 4.07 times 10 to the negative 19. You can put it in if you want to, but don't put the negative into this formula. You don't have a negative frequency, so it doesn't do anything. 6.626 times 10 to the negative 34, which would come out as being 6.14 times 10 to the 14 hertz. Walding throws in a little bit extra there saying it's a blue line. However, I don't generally think about what's what I'm looking for here. I generally don't think about frequency in terms of color. I mostly think about wavelength in terms of color. Maybe I should update that in my head, but part 3 wants us to, or part C wants us to work out the wavelength anyway. So let's work out the wavelength. Remember, wavelength is V equals F lambda. So we're going to have V over lambda equals wavelength. Velocity is 3 times 10 to the 8 divided by 6.14 times 10 to the 14 is going to equal 4.88 times 10 to the negative 7 meters. Okay, now the second part of it, that's part 1 there, is wants it in nanometers as well. Remember, nanometers is 10 to the negative 9. So this is already a small number. I'm going to jump my decimal down 2 places. So that would become 488. Okay, it's jumped 2 decimals times 10 to the negative 9 meters is 488 nanometers. Okay, and that case, yes, that's definitely in the blue region there. All right, so that's about as complicated as you get from an energy level diagram. The hardest part really is reading the side of it and making sure that if it's in electron volts that you do the conversions. Okay. In fact, if you take those numbers and do it, you've got 12.8, convert that into what's what I'm looking for? Into joules, and 10.2, convert that into joules, take the difference, and you'll find the difference there, the delta E, the emission, is the same. Note, 12.8 and 10.2 would not convert to these numbers. Okay, obviously 12.8 is higher than that, but we said 2 was higher than this. This is saying that's the energy from falling into it. This is saying that's the energy taken to get it up to that level. But if you look at the difference between 12.8 and 10.2 is 2.6. Which if you plug into a calculator, there we go. So there's the difference, 2.6 times 1.6 to the negative 19. You get 4.16 times 10 to the negative 19, which is, in this case, very, very close to that. And if you go look at page, where is it? Page 337 of your textbook, it shows the transition for a 4 to 2 is 4.09 times 10 to the negative 19. Okay, so that's these numbers, and should have a few more decimal points on them, but it doesn't matter whether you're dealing with electron volts or you're dealing with what's what I'm looking for. It doesn't matter if it's in electron volts or it's in joules. What you need to realize is that it's still saying the same information, just presented in a different way. Okay, and that if you go from, and as you can see on this picture, it's showing to you here that if it falls in, that's the difference in that is going to be how much it emits. While to go from there to there, that's how much it has to absorb in order to make that transition. Okay, so in this video we have done the following. We have described Bohr's model. We've described how Bohr's model fixes the limitations of Rutherford's model. You just need to describe that, by the way. That's the criteria in the syllabus. You don't need to explain it. You do need to explain hydrogen emission spectra using Bohr's model. So that's that fixed angular momentum, and the transition, meaning is an emission or an absorption of energy. For your entrance up to class, please complete questions 1 to 5 in chapter 12.2 and copy your answers into the 4.2.12 space on eLearn. Thanks very much for listening. Have a great day. Bye.